The James Webb Space Telescope might have identified the biomarker of extraterrestrial life on K2-18b. Specifically, it detected hints of the sulfur compound dimethyl sulfide, which is commonly produced by organisms on Earth. But how did the researchers manage to identify potential biomarkers in the exoplanet's atmosphere in the first place? Could this discovery finally answer humanity's oldest question, whether we are truly alone in the universe, with a clear no? And, if extraterrestrial beings indeed exist, why haven't they made contact with us? This question reflects the simple yet intriguing essence of the Fermi paradox, which was proposed in 1950 by physicist Enrico Fermi and addresses the apparent absence of extraterrestrial neighbors. One would think that the universe has provided sufficient time for numerous civilizations to develop. Yet, officially, we have no sign of cosmic peers. This, despite countless clips circulating on the internet showing mysterious flying objects that appear out of this world, and despite claims by individuals like David Grush or Bob Lazar, who allege that the U.S. government has been running a secret UFO recovery project for decades. Before delving too deeply into these controversial theories, let's stick to the officially confirmed facts. Despite all the pioneer golden records and wow signals, evidence still tells us that Earthlings are the only known life forms in the universe. Isn't that strange, given the countless star systems in the brilliant night sky? Is it even possible that Earth is the only celestial body in the universe that harbors life? Many experts answer this with a clear no, including Tom Westby and Christopher Consolis from the University of Nottingham. As part of an astronomy study, they concluded that 36 highly developed civilizations could be present within the Milky Way alone. The two researchers explained that their lack of contact with us is likely due to the vast distances separating them from us, averaging about 177,000 light-years apart. Just to clarify, a light-year is the distance that light can travel in a vacuum in 1 year, a staggering 9.46 trillion kilometers. While theoretical astronomy studies are valuable, are there also more practical approaches to this significant subject? Yes, there are. As you may know, the James Webb Space Telescope has been probing the deepest secrets of the universe with its infrared capabilities for 2 years now. It has reminded us repeatedly of the flaws in our previous understanding of the cosmos. As the most powerful space telescope in history, Webb could theoretically detect the heat of a bee on the moon's surface from Earth. However, the telescope, which was specially designed for infrared astronomy, is more interested in unveiling fantastic images from the depths of space than in tracking insects. The James Webb Deep Field and the Pillars of Creation images have shown us extraordinary details of the universe. Since its scientific mission began in the summer of 2022, Webb has also raised several mysteries. According to data gathered, Webb has now discovered a series of early galaxies that appear to be too large for their estimated age, just a few 100 million years after the Big Bang. This stands in stark contrast to current cosmological theories. Additionally, Webb's data is expected to deepen our understanding of the so-called Hubble tension, our yet unsolved mystery regarding why the universe is expanding faster than our models permit. Among Webb's discoveries is an exoplanet called K2-18b, which is quite unique. Located in the constellation Leo, about 125 light-years from Earth, this planet is suspected of hosting a fully developed ocean world. These Hycean planets only exist in theory, though a habitable, water-covered exoplanet is still awaiting official confirmation. Nonetheless, current data strongly suggests that K2-18b could indeed be a water-rich environment. Previous observations from the Hubble, Kepler, and Spitzer space telescopes indicated that the planet's atmosphere contains water vapor. As we know, the presence of water in a liquid state is a crucial prerequisite for life as we know it. Since K2-18b orbits within the habitable zone of its host system, the necessary conditions for life are indeed in place. The exoplanet orbits its host star, the cool dwarf star K2-18, at a distance that allows for the presence of liquid water. The distance between K2-18b and its star is only about 0.14 astronomical units, which means K2-18b takes just 33 days to orbit its star. However, since the star emits significantly less energy and heat than our Sun, K2-18b receives almost the same amount of radiation as Earth. In terms of mass, however, the differences are much greater. The exoplanet has 7 to 10 times the mass of Earth and is therefore termed a super-Earth. It's worth noting, though, that this term refers only to mass, not to habitability. Is there extraterrestrial life on K2-18b? We have known of the existence of K2-18b since 2015, but that its atmosphere might contain dimethyl sulfide, DMS, is something we only learned recently. On Earth, DMS is typically produced by living organisms, especially microorganisms like phytoplankton. DMS is also the primary source of sulfur in the atmosphere and acts as a cloud seed, contributing to the characteristic oceanic scent. The fact that Webb's data gathered with the NIRSpec, near-infrared spectrograph, included the spectral signatures of methane and carbon dioxide, as well as those of DMS, was described by lead researchers from the University of California, Riverside, as the cherry on the cake. If astronomers truly succeeded in identifying DMS on K2-18b, it could strongly indicate the presence of extraterrestrial life. Why, then, are scientists still exercising caution? The reason the existence of extraterrestrial neighbors hasn't been formally announced is primarily that the detected DMS signal wasn't particularly strong. It only emerged when researchers analyzed the Webb data in a very specific way. To further test these findings, the scientists decided to recreate the potential water planet and its biochemistry using several models. They simulated the hypothesized ocean and atmosphere on the planet, then examined how much DMS the organisms there would need to produce for it to accumulate in the atmosphere. The surprising result of this research showed that biogenic sulfur gases could indeed accumulate to detectable concentrations on such hydrogen-rich planets. However, this would only be possible if the life forms on K2-18b were significantly more productive than their earthly counterparts, producing DMS at a rate multiple times higher than on Earth. This necessity stems from the fact that a large portion of DMS would break down immediately under infrared radiation due to photochemical degradation. However, if concentrations were high enough, a plausible scenario on an ocean planet, the degradation products of DMS would have a protective effect, with molecules like dimethyl disulfide or methanol acting as a shield for the lower atmospheric layers and preventing further breakdown of DMS. Is it possible to get a clearer sense of the actual DMS occurrence on K2-18b? Fortunately, it is, though not with Webb's NIRSpec. The DMS signal captured by NIRSpec appeared in a spectral line at a wavelength of 3.4 micrometers, which overlapped with the methane signal. To more clearly distinguish these molecular properties, scientists plan to rely on Webb's MIRI, mid-infrared instrument, in the future. This instrument operates in the mid-infrared range, exactly where DMS and its associated byproducts leave their signatures. Unless something unexpected happens, researchers aim to unlock the secrets of K2-18b's atmosphere by the end of this year. We may soon know what the atmospheric markers of this distant world truly indicate, and possibly even whether we are alone in the universe. Let us know what you think in the comments, and show us that we're not alone in the YouTube universe by liking and subscribing so you never miss another update from us. See you soon.